Okay, hopefully everybody can see that okay. Great. Good morning, everybody. Yeah, I hope that you're all sitting comfortably, whether you're in your classroom or at home, and that you're excited and ready to learn about how we map the seafloor around Antarctica, and in particular, these deep channels close to Thwaites Glacier. Just a small caveat with this talk that it was designed for people who are 10 years old or older, and I have a 10-year-old daughter, so I just thought about what she might like to see and what she might understand about what I'm saying when I was designing it and trying to think about what to say. So just bear that in mind as we go along. So my name is Kelly Hogan. I'm a research scientist. I work at the British Antarctic Survey, and we're based in Cambridge in the UK. But as part of my job, I actually get to go on research ships to Antarctica. So the one in the picture that you can see in front of you is the one that we've been on for the past 2 years to go down and study Thwaites Glacier. She's actually an American research ship called the Nathaniel B. Palmer. And this picture was taken from a drone, which took off from this green area here, was flying around, and then looked back at the ship. So you get this really beautiful picture of the ship. We're all sitting down here working on computers, busily working away. And in the background there is Thwaites Glacier. So a really, really pretty image. I was trained as a geologist, which to my 10-year-old daughter seems to mean that I like rocks and that's it. But actually, what a geologist means is that I'm interested in the earth and how it works and what it is made of. But obviously I work on ships and I work around Antarctica. So I'm interested in the seafloor, what that's made of and how it interacts with Antarctica, with the ocean and with the ice there. So what exactly is the research that I do from a ship? Well, basically, I said I study the seafloor, and when we go out and survey and work on our ships, we actually just go out and measure how deep the seafloor is. And what I want to do with that is to build up a picture to be able to make a 3D map of the seafloor and look at the different shapes that we see and potentially also what it's made of. And this is just like a map of how high the land is. So if we look over here on the right-hand side, you can see a map of the UK. And sorry for people who are not from the UK, but hopefully everyone can recognize where we are. The white areas are the highest land areas, and they sort of look like snow up here in Scotland on the mountains. The mountains are these brown and yellow areas, and the hilly areas go down like this. And the low areas close to sea level are the green areas, all around the coast down here. So that's a picture of a 3D picture of the land. I do the same looking at the seafloor. And you can actually do this yourself from home using things like Google Earth. So I'm going to try to show you what I mean. I'm going to click on this and hopefully it will just pop up. So here is Google Earth loading, and it's really a fantastic tool that you can use, from the comfort of your house or from your classroom. And what you get is a globe, and you can spin around and look wherever you want to. But I'll just zoom in on the UK. So that's exactly what we just saw in that last map. And you can see, the green and brown area is the land, and the light blue area all around the UK is quite shallow water, so it's not too deep. And then if we go off to the middle of the Atlantic Ocean over here, we can see it gets darker blue, and that's much deeper water. But if we zoom in, we start to see a lot of really funky features. So we start to see these wiggly worms, these channels that are cut into the seafloor, and all of these different shapes. And actually that tells us something about not only what a seafloor is made of, but what's going on there, how things are moving around and how it's being shaped. We can also sort of just take this opportunity maybe to have a look at how far away from the UK Antarctica is. So if we go all the way down through the Atlantic Ocean, through there's South America, all the way down to the bottom of the Earth, and we get down to Antarctica down here. And now you can see just how far away Antarctica is from the UK. It's about 10,000 miles. It would take 20 hours of solid flying to get there. Right, let's get back to it. So like Sarah said, I want to talk to you about some of the research that I've been doing as part of the International Thwaites Glacier collaboration. Our project is called the THOR project, which sounds really cool, but unfortunately it's not this guy and it's nothing to do with who he's fighting right now. It stands for the Thwaites Offshore Research Project. I study the seafloor, so I'm looking off the shore. So that's what we're talking about here with a Thwaites Offshore Research Project. So we had a look on Google Earth a minute ago. Where exactly is Thwaites? So we went down to the bottom of the Earth and we saw where Antarctica is. If we look, let me just turn on my laser pointer. So if we look at Antarctica over here, you can see where Thwaites Glacier is. It's actually on what we call the western side of Antarctica, in West Antarctica. And it's this whole big red blob over here. Now remember that Antarctica is covered in ice, a really thick ice sheet, and that flows down from the middle of the continent out towards the edges to the sea. So Thwaites Glacier is this big red blob, and it's flowing from the middle, from the T of Thwaites out to the coast here. It's quite hard to know how big that red blob is in reality, because how big is Antarctica? So if we put that red blob next to a picture of the UK, you can see that actually Thwaites Glacier is a really massive area, completely covered in ice, all moving towards the ocean. It's about the same size as about half of the UK, or the state of Florida, if you live in Florida, if you live in the States, for reference. So, you know, it's a really massive area. But, you know, why do we need to think about what's going on at Thwaites Glacier? Why are there so many scientists interested in it right now? Well, we've all heard of climate change. We all know that the Earth is getting warmer, and it's getting warmer not only in the air around us, in the atmosphere, but also the oceans are getting warmer too. And what happens as the Earth gets warmer is our glaciers and our ice sheets are vulnerable to melting. You know, they are shrinking and getting smaller. So if we think about Antarctica by looking at this picture, this sort of dummy diagram over here, what happens there is that snow falls down on the middle of Antarctica in layers, and they get buried. Eventually they turn into ice. That glacier ice flows slowly down the hill towards the ocean, towards the edge of Antarctica, like I showed you with Thwaites Glacier. At the edge of Antarctica, we can lose ice in two ways. We can either chop off great big icebergs from the edge, and they float off into the ocean, eventually melt. Or you can melt the top of the ice, and then that meltwater runs into the ocean like a river. So let's take a little look at Thwaites Glacier, you know, what it actually looks like where it joins the sea. So this is sort of just a zoom in over here of where we are. So remember, ice is flowing down into the ocean over here. And then I can hopefully start this video for you, which basically shows how Thwaites Glacier behaves. These are satellite images. They're taken from satellites from space every year. And you can see the year in the top right-hand corner of your screen. And what you can see, hopefully, let me just put the laser pointer back on, is the bit at the bottom of the screen is moving quickly towards the sea. And let me just wait for that to start up again. Is moving quickly towards the sea, and eventually these chunks of ice, or these big icebergs, break off and move out into the ocean, where they're going to eventually melt and add water to the ocean. And this upper top part of Thwaites is pretty stable and doesn't change that much. But what does it look like when we're actually there? Well, this is a picture of what it looks like to be at Thwaites Glacier from our research ship. And you can see it's a really high cliff, really craggy looking thing. And that's because there's always bits breaking off into the sea. It's about 30 meters tall, which actually, you know, it doesn't mean, maybe might not mean that much to you, but it's about the same height as a 7-story building. So there's really, really massive features. And if you remember those big bits of ice that were being chopped off into the ocean, they look like this, and they could be 30 meters tall, or the same as a 7-story building, or sort of 10 or 20 football pitches long, just floating past you. So much bigger than the ships we're on, and really, really huge features. And if you want a little idea for scale, then here is an inflatable ship that we sometimes send people off to do work from. And you can see how small they are compared to the features that we see around Thwaites Glacier. So Thwaites Glacier, you know, why are we so worried about this particular glacier? You know, the Earth is getting warmer, all of our glaciers are melting and are shrinking to some degree, you know, but why are we so worried about Thwaites? Well, we're worried because Thwaites is shrinking really fast. We know from satellites that can measure how fast the ice flows into the ocean and also how high the level of the ice is in Antarctica, that Thwaites is getting faster and it's getting thinner. So basically we're losing more and more ice into the ocean as time goes on. You know, this picture over here just shows what satellites have found, and the red circle means we're losing ice. The blue circles mean actually that Antarctica is growing a bit. You know, there's not very many of them. They're quite small. And the bigger the circle, the more ice we're losing. And so what we can see is that actually from Thwaites Glacier, which is in this big yellow circle here, is that we're losing a lot of ice. Now, every year, Thwaites is losing 50 billion tons of ice. That's 50 with 9 zeros. It's a lot of ice. And we also know that this rate of losing ice is double what it was 30 years ago. So as our climate is getting warmer, we are losing more and more ice at a faster rate from Thwaites Glacier. Now, 50 billion tons is a bit hard to imagine what that really is, but for those of you from the UK or who've heard of the River Thames and visited London, you know, this is about 50 billion tons of ice is about 25 times as much as what goes through the River Thames and out into the ocean every year. So it's 25 times everything that comes out of the River Thames and goes into the ocean every year. It's a lot of water. And of course, all that water and ice, when it eventually melts, goes into the sea, and that basically raises the level of the sea. You know, if that whole area of Thwaites Glacier melted, then our global sea level would rise by 65 centimeters. You know, what does that actually mean? Well, you know, it's about half a child or above the knees of an adult person. And that is if all the ice in Thwaites Glacier melted. So that whole area covering half the UK melted, then our sea levels would go up by 65 centimeters. You know, and we are not saying that's going to happen today or even in the next 20 years or 40 years, but we do need to know how fast it might happen so that we can help people that live close to the coasts in our coastal cities and communities to help them plan for the future. So why are we so particularly worried about Thwaites Glacier? Well, one reason that we need to think about the ocean and we need to think about and why Thwaites is retreating so quickly or shrinking so quickly is because actually most of the melting at Thwaites is being done by warm ocean water. So I told you that the oceans are getting warmer. There's a very strong warm ocean current that moves around Antarctica, and more of it is getting close to Thwaites Glacier and actually melting the underside of it. And this is sort of helping Thwaites to melt and to shrink. And this is a big problem at Thwaites in particular because most of the Thwaites Glacier actually sits on land that is under the water. So if we take off the whole of the Antarctic ice sheet from Antarctica, then what we're left with is this map over here. So that everything that's brown or green is above sea level. Everything that's blue is below sea level. And you can see that Thwaites Glacier is actually all sitting in blue areas. So it's all below sea level. So if the ocean is what's causing Thwaites to melt faster, then as you expose more and more of Thwaites to ocean water, because it all sits in the ocean, then you can melt more and more of it. And this can basically lead to a problem that can't be reversed. So if that wasn't really clear the way I explained it there, there's a really cool, nifty online tool that you can use to actually explore the area around Thwaites, including looking at how deep it is and how it sits below sea level. So hopefully if I click on this now, this will just start again. And we start again with that really nice globe of the Earth, and we travel down towards Thwaites Glacier. And if I press start, now we've traveled down, here's Antarctica, here's Thwaites. So if I press start and then I close this, you can see all the different projects of the International Thwaites Glacier collaboration here. I'll just turn them off. But if I press, why do we study Thwaites and why is Thwaites vulnerable? And then I say, look under the Antarctic ice sheet. I can show you exactly what I was just talking about. Here is the Thwaites area, that black outline, and you see all of those blues and dark blues showing that most of Thwaites actually sits underwater, and so how vulnerable it is to that ocean warming. And you can do that at home yourselves. There's lots of good stuff in there to look for. Right, so let's get back to THOR. Unfortunately not Chris Hemsworth THOR, but let's get back to THOR. And here's just another picture of the beautiful Nathaniel B. Palmer ship that we were on. It was actually taken by people who went off to an island to do some sampling, and they were looking back on the ship. And here's a picture. This bottom one is looking from the front of the ship as we go through the ice. So that's sort of what it's like to get to Thwaites. So what do we need to know? Well, actually, we've talked about how warm water is one of the big problems for Thwaites Glacier and how it melts the ice there. So we need to know how much warm water is getting to Thwaites, and we need to know how it gets there. In order to do this, we need to know how deep the seafloor is, and we need to know the shape of it. Are there really big channels that just take that warm water towards Thwaites, or are there things in the way, like underwater mountains, that actually stop that water getting there and doing that melting? Over here on this side of your screen is just another picture from Antarctica to get your eye in. The blues are the deeper bits of the seafloor, the reds are the shallower bits. And this is just a beautiful image where ice has gone out and scraped the seafloor in the past. But this is the kind of 3D map that we're looking for at Thwaites Glacier. But how do we actually do it? Well, we use sound. Sound travels really well through water. So we basically send out a ping or a pulse of sound from the bottom of the ship, and then we listen for the return, for the echo of it coming back to the ship. This is exactly like if you're in a cave or in a rocky valley and you shout out and then you hear the echo of the sound coming back to you. It's exactly like that. So then if you imagine this ship going along and sending out sound to the seafloor as you go along, and then listening back to the returns, then we can convert that into the depth, and we know how deep the seafloor is below us. But do you remember, we want actually a 3D picture of the seafloor. We want that cool, colorful 3D picture that shows us the shapes of the seafloor. So actually we use lots and lots of different beams or pulses of sound sent out from the ship in a fan. And they go out down to the seafloor in this fan, and then they echo back to the ship. We record that the time they come back and convert that to depth. Now, if that might seem, oh yeah, and also, so this is a process called multi-beam bathymetry, because we're sending out many beams of sound to get the bathymetry or the depth of the seafloor. So if that sounded a bit confusing, hopefully these images will help you understand it a little bit better. This is one of our the British Antarctic Survey's research ships, and this is a picture of how that fan of sound works to tell us, to help us map the seafloor. So you get these many pings or chirps of sound in a fan going down to the seafloor. They reflect back, we listen for them on the ship, and then we convert that to depth. So as we go along, we actually sort of mow the lawn and build up a 3D picture of the seafloor. So we call it mowing the lawn when we're on the ship. Hopefully we're a little bit happier than this dude over here. I don't know why he's so unhappy about mowing the lawn. But if you look at this bottom picture on your bottom right, you can see a ship going back and forth and gradually building up a picture in 3D of what the seafloor looks like. So in the last 2 years, myself and the rest of my team members from the THOR project have spent 4 months at Thwaites Glacier collecting these seafloor data. That's 2 months in each of the last 2 years, and this is just another picture looking from the front of the ship as we went along the front of that cliff at Thwaites Glacier, mapping the seafloor. Then we also spent a lot of time, many months, both on the ship and when we came home, cleaning the data to make a really pretty picture of what it looked like. Here's a picture of all of us gathered around the data screens on the ship as the data was coming in. And you can see here, the guy is pointing to us, mowing the lawn and adding these stripes of color to our picture of the seafloor. So let's just remember what Thwaites looks like, at where it joins the sea. There's this big floating part at the bottom and this more static part that doesn't really change that much on the top. But we need to know how much warm water is getting underneath these floating parts and is actually doing the melting. So what do we find? Well, this is what we knew before we went to Thwaites in 2019 as part of the THOR project. So what you can see, again, to get your eye in over here is the floating part down here where my laser pointer is. And there's that static part that doesn't change too much up here. The ice is flowing this way across the page with the arrow out into the sea. So this is one of these 3D maps. Blue is deeper, red is shallower. And what you can see is, we had an idea of these deeper channels that might take warm water to Thwaites, but we didn't have a great idea. It's quite fuzzy. We can't see the exact pathways that might be used. So then we went there on our ship, had a great time in 2 cruises, spent 4 months doing this mapping, using our multi-beam bathymetry tools. And this is what we got. We got this amazing picture, new picture of the seafloor in so much more detail, so much better resolution than what we had known before we went there in 2019. So what you can see, hopefully, is these really dark blue, deep channels that are able to carry water in towards Thwaites Glacier. You see this one is a really obvious one here. There's also a nice deep area over here that might carry a lot of warm water, but also these smaller channels that actually funnel the water very close into the glacier here and here. I've added some arrows here. So now we can really know in a lot of detail what the pathways of this warm water might be. If we look at it in 3D, if we sort of spin it around and look in 3D, then we get this picture. So here is that floating bit of ice. Again, you can see it here. Here are those small channels moving in towards Thwaites Glacier. And, it's a bit hard to say, I'm telling you dark blue is deep and the red is really shallow, but it's quite hard to know exactly how big these features are. So let's use something that we can all identify with for scale. So let's use the Eiffel Tower. The Eiffel Tower is 300 meters tall. So each one of these deep blue channels is about 2 Eiffel Towers deep. So it's 600 meters deep, super, super deep. And that means they can carry a lot of warm water potentially in towards Thwaites Glacier. So let's just do a tiny, tiny bit of maths with all the really good seafloor data that we collected. So remember, we wanted to know how much warm water gets to Thwaites Glacier and how it gets there. And we did this mapping and we mapped these really big, deep channels leading underneath Thwaites Glacier. And they're much bigger and much deeper than actually we thought they were. So if we take, just go back to this one. If you take a line, hopefully you can see my laser pointer on this white line in the bottom right-hand side of your screen across the channel, and you look at the shape of the seafloor there, this is what we knew before we went there in 2019. So this is what we thought the seafloor looked like. And that means that, and here are some of your Eiffel Towers for scale. You can see exactly how deep those channels are. And that means that this much warm water can move through those channels towards Thwaites Glacier. The warm water actually only sits below about 500 meters. That's why it's only about half full, but it's the deepest part of the channels that are the most important. And then when we went there and did our mapping, this is the real shape of the channel. So you can see all these extra bits that we've missed out carrying warm water. So this is the actual amount of warm water that's going towards Thwaites Glacier. And these channels, we now know, about 40% bigger. So the area of them are about 40% bigger than we had thought previously. And because of how the hot water sits in these channels, there's actually more heat in the deeper parts. Actually, they can carry almost double the amount of heat towards Thwaites Glacier. So, that's pretty much it for what I want to talk to you about how we map these great big channels using sound in the last 2 years. But, it's important to remember that, we went to a place at Thwaites Glacier that no one has ever been to before. And the reason that we got to go there and do this work really is because Antarctica's ice is shrinking, and some of these places are opening up to ships that were never being able, we've not been able to access before. So it's not, although it was good for our study, it's not great for Antarctica. Just want to remind you that we used sound to make these 3D maps of the seafloor. It took about 4 months to do all of this work, plus a lot more time and effort at home. And we mapped an area of about 2,000 kilometers squared, which probably doesn't mean that much to you. It doesn't mean that much to me. But it's nearly 300,000 football pitches, if you can think of a football pitch. So it's a huge area. And basically what we found was bigger, deeper channels leading to Thwaites Glacier than we had previously thought, and that they can carry maybe twice as much heat to the glacier than we thought previously. Oh, that's just the picture of the sound, the fan of sound going to the seafloor again. But there's still a lot that we need to know. We need to know what's in those channels, and we need to know which one of them hold warm water and how it moves around, because maybe some of them don't have warm water in and they're not actually causing melting. So we need to go and measure the temperature of the water in these channels. There are lots of different ways that we can find that out. We can use instruments that we lower down to the seafloor, like this one, and they measure the temperature of the water and also how salty it is. So we can see where that warm water is sitting. We can use underwater robotic vehicles in places that we can't access very easily. So where there's lots of ice still around, we might be able to send one of these robots underneath. We can also use, and people do, use instruments that they tag onto seals. And these also measure the temperature and the saltiness of the water. No, don't worry, these are all very friendly and they fall off after a certain amount of time. But when the seals go and dive for food, they can measure the temperature of the water where they are, which is actually really cool. All of these things are what oceanographers do and other types of scientists do. I'm a geologist. This is what the oceanographers do. But the message here really is that we all need to work together to understand what's going on in Antarctica, but across the planet, to understand what's going on with climate change. Just wanted to start this one video. Maybe you don't love the idea of going away to sea, and maybe you're more interested in playing computer games or in programming. The shape of the seafloor and those measurements that the oceanographers might make of where the warm water is are the kind of information that we need to run computer models. So this top one, maybe you can focus just on the top screen, is just the temperature of the ocean water as it gets towards Thwaites Glacier. So Thwaites Glacier is down here at the bottom. The floating part is here, and you can see the browns and other warmer water, and you can see it circulating and moving under there. So we need to know where those channels are and plug that into these models to be able to understand what's going to happen to Thwaites in the future. So again, I'm a geologist, I need the oceanographers, but I also need the computer modelers. We all need to work together on this. Obviously, I just want to say quick thanks to everyone. This is our THOR team down here. There are lots and lots of people that go into doing this work. None of it is done. I did not do it all myself. None of it is done without lots and lots of different people involved. There's 2 cruises worth of people, which you can see. There's just one of our cruise photos down here. There's everyone on the ship close to Thwaites. So there's lots and lots of people involved. So we need to work together, and you also need lots of people. Okay, I think I've talked a bit too long, which I'm really sorry about that. There are some really good online resources available, so I'll leave this up, but maybe we can just move on and see if there are any questions for me.
Thanks, Kelly. Was really good, actually, really good clear explanation of things, and good demonstration of other resources that people can use, and especially for people like me who aren't scientists. So it's good to have a sort of general overview. So let's move on to some questions, if we can. I've actually got one here from Bridget in Holland, who says, why is the deeper water warmer? So at the beach, the upper level is warmer.
Yeah, that's a really good question, and I didn't go into too much detail about this because of because who we were sort of pitching at. But if you the deeper water is warmer because it's also saltier. So it's salty enough to make it heavier or more dense than the water above it, which is colder and fresher. So even though it's warmer, I know what you mean, because warm water, you think of warm things rising up above cold things, but because it's super salty, like if you imagine stirring salt into a glass and you see that really heavy water sinking to the bottom, it's like that. So even though it's warm, it's so salty that it sits in the deeper levels.
And we've got a question here, says, from Lizzie, saying, is the use of sound disruptive for marine wildlife such as whales, that they use sound for navigation and communication?
Yeah, that's a really good question as well, and it's something that we have to think about when we use acoustic instruments, so any instruments that use sound. There have been some studies. It's quite hard to study this because it's quite hard even to know how whales behave and move around. So then it's quite hard to know actually the effect on them that any of these things are having. You know, it is generally thought that the kind of work we do, the type of sound we use, is not very bad for whales or for seals. In fact, they seem more curious than they don't run away from us. They in fact seem more curious about ships than they seem disturbed. But it is something that there's a whole field of people, of marine mammal observers and marine biologists that look into it. And there's also acousticians that study how sound works in water, and they together work out whether they think there's a big problem. But we are quite careful with our instruments and how we use them so that we don't affect wildlife.
And we've got a question here, is there a way to date the features that you map? And if so, how old do you think they are?
Yeah, that's a really excellent question. I mean, there's a whole nother part of the THOR project that looks at dating the seafloor muds and sands that we find down there. So it's quite easy to date using radiocarbon, which is, you know, a type of carbon isotope or a type of carbon in the seafloor muds. It's quite easy to date anything after the ice. If you imagine an ice used to be there and then retreated from an area, and then all these critters that live in the ocean and fall down to the seafloor, they contain carbon. So you can date when the ice left the area, but it's actually quite hard to date the rocks that make the big channels. What we know from looking at the rocks on land and from from dating some of those is that these features are probably really old features. The channels themselves are probably millions and millions of years old, and then water and ice has helped sort of shape them. But it's actually really hard to get a date from that rock itself.
Okay. Okay, so we've got a primary school who's with us, year 6 at Leamington Primary Academy. And they've asked, you know, have you found any other forms of pollution in the ocean around the glacier?
That is a good question. And there are lots of people. I haven't seen pollution at Thwaites Glacier in particular there, but I also don't look for, I'm sure you've heard of plastics in the ocean and something called microplastics. And these are really, really tiny bits of plastic. And they are definitely there in the muds and the sands that are on the seafloor around Antarctica. Not in very high levels, but they are there. I would say Antarctica is a bit cleaner because it is very far away from the big cities and from people really. So it is a bit cleaner than the Arctic, for example. So I also work in the Arctic, close to Norway and Greenland. And I've been on ships before where they've sent an underwater robot to go down and look at the seafloor, and they had a camera with it, and they went down to a very remote area, lots of ice around, and the first thing that they saw was a plastic bag in the muds and the sands. And that was really, really upsetting and sad to see, but the Arctic is probably more polluted than the Antarctic is right now. But we obviously don't want it to get any worse, so there's lots of people working to protect it as well.
Thank you. So we've got Ollie and Harrow Barrow Primary School. That's a good name for a primary school, isn't it?
Harrow Barrow, yeah.
How deep is the deepest part? So I know you had a couple of Eiffel Towers, but how deep would the deepest part be?
Yeah, that's a good question. If you remember when I showed you that if you take the ice off Antarctica, it gets deeper and deeper towards the middle bit of Thwaites. But the deepest bits that we mapped were about 1,400 meters. So that's about 4.5 Eiffel Towers for scale. So, you know, it's super, yeah, it's super deep there. And the problem is, because it gets deeper and deeper, is that then you can get more and more of that warm water getting close to Thwaites. You know, that really is the problem. So yeah, that's an issue for Thwaites.
Okay, so Ben's asked whether you ran into complications with scanning the seabed with icebergs getting in the way or bad weather. So when you're mowing the lawn, did you run into any problems?
Yeah, that's such a great question, because we use sound that we send down to the seafloor from the ship and then it comes back. If you have a lot of ice around, so those big icebergs, we can't go anywhere near them. They're so big, they would damage our ship, we would be in trouble. But you can go close to sea ice, that's where the ocean has frozen because it's so cold in Antarctica. You can, with these ships, move through sea ice. But if you do that, you make a lot of sound, and that interferes with our sound that we're sending down to the seafloor and comes back again. And so, you know, that's not good for us. Thwaites, you know, I showed you that video of how the ice moves out to the ocean, and actually there's quite a lot of floating ice around almost all the time. The first year we were there, it was pretty open, and we were like, this is an amazing time to collect data. And we did a lot of mowing the lawn that year because it was open water, and that's really unusual for Thwaites. The second year we were there was much harder to work for us mowing the lawn, and actually we had to do tiny patches and then leave an area because a big iceberg was chasing us down. So it was yeah, it was much harder to work the second year, but that's why it's also really important. You know, you can't just go to these places once. You have to do a big program of work. That's why, you know, our Thwaites program that we're talking about is 5 years, and people are going back to Thwaites multiple times to get what they need.
So following on from that, actually, Faz in Malaysia, I don't know if you mentioned this before, but it said in 2020 you used multi-beam. In 2019, was that the same, that you used that for both years that you were there?
Yes, we did use multi-beam bathymetry all the time. So like I was just saying, it sort of follows on from the last answer. The first year we had a lot more open water, so we could map better, and we did a lot of mapping that year. And the second year we actually did a lot of sampling. Like, I didn't talk about it today at all, but a lot of the people that work on the THOR project actually are interested in collecting the seafloor muds and sediments, and the layers of muds and sands and sediments can tell us about how Thwaites behaved in the past, like whether it was chucking out lots of icebergs, whether it was melting more, or what was happening to it. So they are interested in those kind of records. And so what we did mostly last year was move around and actually take samples. So we send basically like a drain pipe with a big weight on the top down to the bottom, fill that up with mud, and then you get those layers in what's called a sediment core or marine core. So we actually did more sampling in 2020 and more mapping in 2019.
Okay, great. So we've got a school in Caldecott in Monmouthshire, and I feel really embarrassed because I, you know, don't know how to pronounce Welsh names, but they are in Caldecott in Monmouthshire, and they'd like to know just generally, what is it like working in Antarctica?
I would say that it is amazing. It's totally amazing. So you remember the pictures that I showed you of what it looks like at the front of Thwaites? It feels so far away. I mean, it is far away, but it feels so unbelievably far away and remote, and it's so quiet, so there's no noise. You know, the only noise is the ship and the stuff that you do, and it's so pristine. You know, there's no litter, there's no industry, there's no traffic noise, there's no anything. And so actually it is just, you know, it's magical to look out at that and to wake up and that be outside your window in the morning. But, you know, it's far away as well. And, you know, every time or the 2 times we went to Thwaites in the last 2 years, we went away for 2 months at a time. And so, you know, I missed my daughter for 2 months, and I missed 2 of her birthdays, for which she'll never forgive me. But, you know, it's a sacrifice that we make to be able to help us understand what's happening there. So, you know, it's far away. Sometimes you feel lonely from your from your family, but actually you have a lot of good people that you work with. Like I said, there's big teams of people, so you never actually get lonely. But yeah, really, it's a very special place.
And so actually tagging on to that, because you were away for so long, we've got Queen Victoria School in Dunblane who want to know how you have enough food and other supplies for the long trips.
Oh, that's such a good, yeah, that's a good question. But you actually wouldn't believe, well, maybe you would. I mean, the ship, it's about 100 meters long and about 20 meters wide. And basically half of that on the bottom is just full of fuel. Actually, the biggest thing is fuel to run the ship. You know, we need a lot of fuel. It's about 5 days of sailing from South America to get to Thwaites Glacier. So that's without seeing any ice, without seeing glaciers, just crossing the ocean. So it's really far away. And so you do need a lot of fuel, but the ship can carry, plenty of fuel. That's not a problem. And similarly, food, the one thing that we do run out of is fresh food. So, we'll start off having salads and fruit and all those good stuff. And then slowly the salads disappear and you start having more tinned vegetables and more dried fruit and those kind of things. And, at the end of 2 months, the fresh supplies are really gone, and you just have to make do. But it's not like it's terrible. People cook for us. There are chefs on board that cook for us 3 meals a day, and there's plenty of food. So, if anything, don't tell this at home, but I probably put on weight when I'm away rather than lose weight. But yeah, don't worry, there's plenty of room for food and fuel.
Okay. So we're going to take a bit of a sidetrack here, because I know you put the photo of the seals up, and we've got a couple of people who've been asking about the seals from Cocoa and Primary, and they want to know how you get the tracking device onto the seals and whether you use any other animals to track.
Yeah, good questions. I should just say before we go into that this is work done by people at St Andrews University, and they are specialist marine biologists and oceanographers. They've been trained for years and years to work with these animals, to do it in the safest way possible, and they have really they work hard to get permits to let them do it legally and safely, so that it's totally approved and everything like that. So I need to say that first. Yeah, it's quite a process. I mean, I don't do it myself, but basically they take one of those small boats out, they find seals lying around on bits of sea ice, and they find one that they think they might want to put a tag on, and then they basically give her or him an injection of anesthetic to go to sleep for a very short time, and then they use glue to stick it onto their forehead like it showed in the picture. And actually what they found was, for cold temperature in Antarctica, the super glue was one of the best things that they can use. But they do it at a very particular time of year. They do it after they've lost their winter coat. No, or is it maybe it's after they've lost their summer coat, and then they glue it on, and then it stays on for a few months, and then the next time they lose their coat, it falls off with that. So they only ever have it on for a few months, and they go, and they are quite happy. They go off and they do their dives and they fish for food, and they go all around, and they don't, and then they lose it in a few months' time, and they've never been any problems with that. And actually, it's been really good for understanding where seals dive to and what kind of food they eat, because actually it's really hard to know what the animals do when they're in the ocean. And so what they can also do is make maps of where the animals get to, and they go thousands and thousands of kilometers away from the beaches where they like to have their babies, and then they come back to that. But it's really amazing what they can do. As for other animals I don't think that they do any, there are people in our building at the British Antarctic Survey that tag birds, for example, to see where they fly to. But that's not measuring ocean temperature, it's just to see where the birds get to and how they behave. But I don't know of another marine animal that we do that with.
So then this is kind of connected to that, if you have got marine mammals. I've got Rodrigo who's asking about, mammals and whales and sound, whether you have a protocol of sorry, let me read it properly. In seismic surveys, they have to use marine animals observer and have protocol to observe the desired area of study. not getting the green light if marine mammals are spotted in the vicinity. So before you start the survey, do you have to follow the same protocols if you spot marine mammals?
We do have to do that if we're doing a seismic survey, like Rodrigo said. And actually last year on our cruise, we were doing some seismic surveying, and we had 3 marine mammal observers. They worked in shift, looking out at the ocean at all times, looking for marine mammals, so seals and whales. And anytime, they tagged anytime and marked anytime they saw one. And if we were running or planning to do the seismics, then you're right, they have to be quite far away from us before we can do that. And if you see one coming near, you just have to stop. So we do that for the seismic work. For the multi-beam bathymetry that I talked about, the sound is low frequency and actually it's low power, and there are not the same rules or regulation. They don't think that they really hurt the animals in any way whatsoever. Not that we think the seismic ones do, but we just think it's louder. So we don't have the same protocols. We do something called a soft startup, which means that you don't just turn on the multibeam and send out loads of sound into the water. It means that you turn it on and it sends out a bit of sound, quieter, and gradually gets louder, so that it shouldn't be so abrupt, and shouldn't worry the animals so much if there are any around us.
So I've got a question here. It says, in your opinion, does the warm water affect the topography of the seabed and cause changes in the future?
That's a good question, and there was one actually on the a question submitted before the talk about black smokers and what the warm water does to the seafloor too. No, we don't think that the warm water is eroding the bed, or cutting the bed or shaping it in any way. So most of the bed and the channels that I showed you are rocky, so that's really hard rock, like imagine a mountain made of granite, really hard rock, and if we tried to take a sample there, you can't really get very much back, and so we know where those areas are, and most of them it is hard rock. So warm water doesn't do enough to cut or erode that or make those channels any bigger. So no, we don't think the warm water does that. Maybe I just answer the question about the black smokers. Now someone had asked whether black smokers, what happens to the warm water that comes out of black smokers, and does it affect the ocean currents? Black smokers emit chemically, sort of heavy chemically warm water, and it's called smoke because it poofs up like that. It looks black because it's full of iron and other metals, and it poofs up like that, and actually because it's so warm it rises up as a plume like smoke. That's why it's called a smoker. And so actually all that water rises up and then eventually it sort of spreads out. But the rest of the ocean, by comparison, is so cold that actually it doesn't really affect the currents that are moving around it. It's more likely to affect the chemistry of what's going on there, because all of a sudden you get manganese and iron and nickel and all of these things getting into the ocean in this one spot and dissolving into the water. And so it's more likely to affect the chemistry and the biology than it is to affect the ocean currents.
And actually, Teresa says, when you say warm water, what is that temperature versus normal water? So what would constitute warm water versus cold?
Oh yeah, that is a great question. And I'm not an oceanographer, but it's not what you and I think of as warm. It's it's 1.5 degrees. So it's cold, but for Antarctica it's warm, and it's warmer than the rest of the stuff that's there. So if you also imagine if you imagine water that's melting, or that's come from melting icebergs, or from Antarctica, from the ice melting, that is fresh water that's super cold. It's about 0 degrees. So even 1 or 2 degree difference is enough to cause a layer of that cold fresh water on the top and the warm salty water underneath. So yeah, it's not balmy.
What we think is balmy, no, like you say. Okay, I'm going to have a question about, what is it like to work on the THOR project, and what sort of opportunities would there be for people to move into this field?
Yeah, it's a good question. I mean, the THOR project is super fun to be part of. Like I showed you the picture that has all of the different people that work together on the project. You know, it's a UK USA collaboration, but we also work with colleagues in Sweden and in Korea and other places. So there's lots of people working together with a common goal, and that actually is really great to be part of such a good team that's driven to understand what's going on at Thwaites and use our kind of science, you know, use the geology to help us do that. What opportunities are there for getting into this science? Well, you know, it's a long career path. It's not like you could just go to Antarctica tomorrow. You know, the ships don't go there. It's really only scientists that go there. If you're interested in this kind of stuff, then do your maths at school, do your science at school, you know, study physics, biology, chemistry, geology, maths, you know, and then look out for, you know, when you start to look at universities, you do something, the thing that interests you. If you're interested in how the ocean currents move around, then look for a course in oceanography. If you're interested in the seafloor like I am, then study geology or geophysics. And there are university programs in the UK and elsewhere that take classes to places in the Arctic, for example, not so much in the Antarctic, but in the Arctic, where you can go and you can look at glaciers and you can be in the field. You can either do it by walking out and hiking up to glaciers on mountains, or you can work on ships for a few days at a time. So if you're interested in that kind of stuff, do that. If you're school age, like secondary school, and you're close to Cambridge, you know, or not, look for, you know, you talk to somebody here about doing a work experience with us. And there's lots of potential ways that you could get involved, you know, by following all of our online information as well.
Great. Okay, so where are we? Sorry. Ben from Lincolnshire. Actually, I don't know if you're going to be able to answer this or not. Says, if all the glaciers in the world melted, where would sea level go up to in the UK?
Yeah, that's a good question. I mean, so Antarctica. Let me have to try to get these numbers about right. If all of the ice on Antarctica melted, it's about 60 meters higher than we are now. If all of Greenland melted as well, it's another, I think it's another 30 meters, plus like all the mountain glaciers. So, I mean, you're talking about 100 meters higher than where we are now. And I don't have a map of that handy, but it's a lot of area that you would lose, you know, from England for sure, like all of East Anglia, you know, gone. If you look at Holland, you know, there's large parts of the continental USA that are in trouble, large parts of Asia as well that are really low lying, you know, like the Maldives, you know, gone, you know, all of these things. But that, you know, to do that it would take quite a long time. You know, it's probably not something we're worrying about in our lifetime, but it is what we're trying to understand how fast it could happen. That is what we don't know right now.
And I've got a question here from Danny saying, have you seen any big calving events from Thwaites? Is this something you have to be prepared for and risk assess as you're then going to mow the lawn and do your work?
Yeah, that's a good question. So I said in 2019 when we were there that we had a lot of open water and there weren't very many big icebergs around. So we spent the first sort of half of the cruise mowing the lawn and taking advantage of that open water. And as we did that, we thought, oh, this is a great place for maybe getting one of those samples of the seafloor muds and sands. And we thought, oh, we'll come back here. So we'll keep doing our mapping and we'll go off and do some other oceanography measurements, and then we'll come back here. And towards the end of the cruise, we started to go back to some of those places where we'd mapped those big channels actually, and we wanted to take new samples. And we found that the whole area was covered by these kilometer by kilometer icebergs, you know, 30 meters tall, absolutely massive, and they were everywhere. And the captain he just said, you know, we can't go there. We can't. And it's because if you remember the movie that I showed, it's not just one iceberg falling off. It's large bits of that floating bit of Thwaites breaking off at the same time. And then all of those icebergs just move around. But each one of those bits is a kilometer by a kilometer. So they're massive and you can't work in that. So even within a 6-week, 8-week period, we couldn't go back to some of the places we wanted to be before. So yeah, it does happen, and actually it's happening more regularly. I mean, the only thing to remember is that icebergs falling into the sea from Antarctica, it is a normal process. So, you know, the ice does have to move, flow downhill to the sea, and eventually it will melt or break off into the sea. You know, it can't just stay there forever, statically not moving. But it's happening faster and faster, and we're losing more and more. You know, that's the important thing.
I think that's probably what we can't get from your video is the scale. Like, you see those bits of ice that are breaking away, but actually the scale of them when you're on the ship and actually being amongst them. Yeah. Okay, so we've got time for one last question I'm going to ask. Volker has asked, West Antarctica is most likely a geological spreading zone. What is the effect of volcanism and thermal water on the glacier?
That's an excellent question. Not a 10-year-old question, that is. That's an excellent question, though. Yes, that's true. There is more geothermal heat in West Antarctica than East Antarctica. What the community is sort of thinking now is that actually that the more heat that there is in West Antarctica has caused more melting at the bottom of the ice sheet than in East Antarctica, which is more frozen to the bed. And that melting, that extra water at the bottom of the ice sheet can do a couple of things. It can either help the ice sheet slide along, so it can move faster, which means it moves faster to the sea, and you can actually, you know, lose more that way. Or you can build up water in subglacial lakes, which eventually build up and then they drain. And when you sort of, you know, and that sort of drains on the bottom of the ice sheet, you know, in between the ice and the rock. And as it does that, that can then speed up the ice flow to the sea. So it is a well-known phenomenon. And actually we can use geology and the records offshore to understand, you know, the last time it pumped out loads of icebergs, was that because of one of these subglacial lake drainage events or not? So yeah, it's well known, but we are still learning about that. That is for sure.
Great. I think we actually probably have to draw it to a close. Unfortunately, that's our hour up already. So
yeah, good fun.